A very good afternoon to everyone. My name is Chandan Kumar, and I'm a PhD student in Electrical Engineering Department in Indian Institute of Technology, Gandhinagar, and I'm working with Professor Arup Chakraborty. Today, I'll be talking about a fiber Bragg grating sensor-based instrumented glove that we are developing for stroke rehabilitation. So, am I audible? Okay, fine. Thank you. So the motivation for carrying this work comes from the fact that stroke has become the second largest cause of death globally. Incidence rate of stroke in developing nations like India is much more than those in developed countries. About 46% of stroke survivors are left with prominent residual disability, which makes them overly reliant on care providers and also severely impacts their socioeconomic conditions. And therefore, it's very important to address this concern. Traditionally, goniometers have been used to assess the range of motion of finger joints in stroke patients, but these devices are difficult to use, are prone to error, and continuous measurement using this device is simply not possible. Tests like box block test, 9-hole peg test, etc. are largely subjective and do not provide sufficient information to physiotherapists to customize the physiotherapy exercises to individual patients. And therefore, an instrumented glove which can measure finger flexor speed, stability of hand functions can become a very important tool for rehabilitation setting. Plus, these gloves, when combined with virtual reality games, can act as an incentive for stroke patients to mass practice these exercises, which can lead to significant improvement in their motor functionality. Now, several instrumented gloves have been reported so far, and many are available commercially. For example, CyberGlove 3 uses flex bend sensors and are in 18 or 22 sensor packages, but the price is fairly high. Another glove that is available commercially is Human Glove that uses 20 Hall effect sensor. An alternative to these are inertial measurement units. In general, optical sensors have been shown to provide better sensor performance in terms of sensor resolution and accuracy. Over the past few decades, the performance of these gloves have been significantly improved, but there's enough of scope to improve them further, and this is where we are trying to contribute. So the sensor design that we propose consists of a fiber Bragg grating as a sensing element and is attached to a spring. So the spring side of the sensor unit is attached onto the dorsal side of the palm, while the fiber end is attached on the phalanx following the joint of interest. So when you flex the finger, this introduces strain in the FBG, and by measuring that strain, we are able to find out the joint rotation angle. Now we've put this sensor on a glove, and with that we also put an IMU on this. So in our experiments, the angle registered by IMU is considered to be the true measure of joint angles, and we calibrate our sensor and report the accuracy of our sensor with respect to the IMU. So we used our own FBG interrogation technique in our experiment. Basically, we use an acetylene gas line and the Mach-Zehnder interferometer transmission spectrum to determine the Bragg wavelength of the reflected FBG spectrum. This work was published in Applied Optics last year. So first we studied the response of our sensor, and for this we placed our sensor unit on a translational stage. By rotating the attached micrometer in clockwise direction, we strained our sensor from 0 millimeter to 10 millimeter in steps of 0.25 millimeters. And then we relaxed it back, again in steps of 0.25 millimeters. Here, the clockwise rotation corresponds to finger being flexed forward, while when it's rotated in anti-clockwise, that corresponds to finger being flexed backward. So in both of these cases, we found very high linearity. We calculated the hysteresis, and the maximum and mean hysteresis turned out to be 0.90% and 0.35%, which are lower than what has been reported for optical polarizer sensor by Wang et al. In 2017. So what does this mean? Whether you flex your finger forward or backward, there would be virtually same response from the sensor. Next, we have used IMU sensor as a reference sensor in our work, and therefore it was necessary to ascertain its accuracy. And to do that, we attached the IMU sensor on one arm of a bevel type protractor, which had an accuracy of 0.08 degrees. And then we vary the angle from 0 through 90 degrees in steps of 5 degrees. And at each step, we take 512 measurements. So there we found out that the mean absolute error and the maximum standard deviation were 0.43 degrees and 0.63 degrees. We found this to be fairly low, and therefore we used this sensor as a reference. This also helps, doesn't constrain the movement of a finger, and that was one another reason we used this. Next, we measured the PIP joint angle of 3 different fingers, index, middle, and ring finger of 4 different participants. And for this, we attached our sensor unit on the glove along with the IMU. Prior to measuring the angles, we performed a calibration. And for calibration, the subject wore the glove and put his hand comfortably on an experimental table, then started bending the finger very slowly. At every 2 degrees of bend registered by IMU, we captured the FBG reflected spectra, and in this graph I have plotted the Bragg wavelength corresponding to the angle measured by IMU. We fitted a line to this, and then we find out the intercept and the slope of this line, which acts as calibration parameter in furtherance of the experiment. Then we go into measuring the finger angles using our sensor, and the protocol is same, but in this case we use the slope and intercept parameters to convert the Bragg wavelength into corresponding angles. So in this graph, I have plotted the angle measured by our sensor corresponding to angle registered by IMU for 2 different subjects, the measurement of PIP joint angle of the middle finger. So in this case, we found a very good agreement between both of these results. For subject 1 and subject 2, the maximum error for 5 repetitions of this experiment came out to be 1.32 degrees and 1 degrees, while maximum standard deviation was 0.56 and 0.52 degrees. In this graph, we have plotted the result for 2 fingers, the middle and index finger, for the same subject. And here again, the maximum error was 1 degrees for both the fingers, and maximum standard deviation was 0.52 and 0.38 degrees. In this table, we have compared the sensor performance, our sensor performance, with the earlier existing sensors. So the mean of the maximum error from all the experiments was 1.26 degrees, and this is smaller than what has been reported for optical polarizer by Wang et al. In 2017, and FBG sensor by Silva in 2011. Similarly, the statistical range and the standard deviation of 1.03 and 0.49 degrees is also smaller compared to earlier developed sensors. Besides that, we are also developing virtual reality games. The focus is to develop specific games that can be played using our glove for the stroke patients. And I'll be showing you 2 videos here. In the first video, you'll see the virtual hand here simply mimics the gestures made by the glove. So we are able to currently detect all the 3 finger joints. In the next video, we have developed a simple breaker game which you can play using our glove. The index and the ring finger are used to stir this paddle left and right, and the middle finger is used to launch the ball. These are not perfect right now, but these demonstrate what we want to achieve in near future. Okay. So we are also working on developing a compact interrogation system that would be low cost and affordable. And currently our system fits in a box of 30 centimeter by 45 centimeter by 20 centimeter approximately. This is very bulky and obviously requires AC power, PC connection, definitely not wearable. So we are trying to reduce its size of components, and we envision to fix it in a box of 10 centimeter by 10 centimeter by 5 centimeter, make it battery power, wearable, and implement wireless data transfer on this. We expect the cost to be around 2 lakhs. In future, we are going to attach multiple of these sensors on a glove so that we can monitor all the joint angles simultaneously. We are also working on developing some focused exercise games for stroke patients that can be played using our glove. And then we'll be finally testing the efficacy of our entire system on healthy and non-healthy subjects. In summary, FBG sensors are potential choice to develop instrumented gloves for medical applications due to the high resolution of 0.1 degrees, high accuracy, high repeatability, and very low hysteresis error that we have achieved. The calibration process is simple because the response is linear, and we are also working on developing a low-cost, rugged interrogation system for our glove. That's all for today. Thank you for your attention.